welcome. Before closing this section for internal direct product, let us have some examples. So, examples of internal direct product. Okay. Number one, uh, we know that the Kleins 4 group K4 contains 4 elements. Let the element be denoted by E, A, B, C. Okay. And the binary operation defined in this Kleins 4 group is like this. Your S square is equal to B square is equal to C square is equal to identity always, and AB is equal to C, BC is equal to A, and CA is equal to B. Of course, it is abelian. So AB equal to C is equal to BA, BC equal to A equal to CB, and CA equal to B is equal to AC. So this is how the elements are related. Now this Kleins 4 group is actually an internal direct product of two of its normal subgroups. If I consider H1 to be a normal subgroup, say EA. Why this is the normal subgroup of K4? Because the index of this, in fact, any subgroup of an abelian group is normal. So let us not think about index. So this is a normal subgroup of K4. And if I consider H2 is equal to identity and B, then this is also a normal subgroup of K4. Now see, every element of K4 can be expressed uniquely as an element of H1 and element of H2. Let us try. Let us choose any element from K4. So you have 4 elements. You have 4 choices E, A, B, C. Take anyone. If you take A belongs to K4, then I can always write, this will imply I can always write A is equal to AE, where your A belongs to H1 and E belongs to H2. Can you express A in any other way as an element of H1 and element of H2? No, you cannot. Because if you, instead of taking A in H1, if you take E, then E multiplied with nothing in H2 will give you A. If you multiply E with any element of H2, it will give you that same element in H2, and A is not there in H2. So you have to consider A from H1. And once A is chosen from H1, you have no other option other than choosing E from H2. Then let us choose B. If you choose B from K4, then you know that B is actually EB. E belongs to H1 and B belongs to H2. And it is very easy to see that this expression is also unique. If you choose C from K4, then C is expressed as AB, where A belongs to H1 and B belongs to H2. And see that this expression is also unique. You cannot express C in any other way. And if you choose identity, then that is very easy. Identity into identity, where identity belongs to H1 and identity belongs to H2. Right? If you want to check it by the alternative definition, you see any element of K4 can be expressed as product of an element of H1 and product of an element of H2. And apart from that, what is H1 intersection H2? H1 intersection H2 is the trivial subgroup identity. So definitely K4 is the internal direct product of H1 and H2. Not only these two, if someone says that yes, I have another normal subgroup H3 which contains identity and C, then also K4 can be written as K4 as an internal direct product of H1 and H3. Similarly, it will be an internal direct product of H1 and H2. And similarly, it will be an internal direct product of H2 and H3. So any two you can choose, you can form internal direct product. So this is one example. Let us see an example from a non-commutative group. So let us go to example 2. Consider the non-commutative group D6. So it contains 12 elements. How it is defined? D6 is generated by two elements A comma B, where uh, say A6 is equal to identity is equal to B square, and BAB is equal to A inverse. What is A inverse? By the way, A to the power 6 is identity. So A inverse is nothing but your A to the power 5. Okay, let me write A inverse. And the same thing is actually the group generated by AB, where A to the power 6 is identity is equal to B square, and BAB is equal to, or someone can write BAB inverse. B inverse and B are same. So this is equal to A to the power 5. So this is D6. Now this D6 is actually an internal direct product of two of its normal subgroup. If we take my H1 is equal to identity S square A4 B S square B A to the power 4B. How many elements? 1, 2, 3, 4, 5, 6. And if I consider my H2 is identity and A cube, both are normal subgroups. Why? Why H2 is a normal subgroup? If you recall, in D4, we have shown that the center of D4 contains E and S square. There probably S square I have not chosen, there Y square I said. Anyway, the symbols are changed only. A is replaced by Y, and Y is replaced by A, and X is replaced by B. Anyway, so if you apply the same technique, it is not difficult to show that this H2 is actually the center of D6. Since H2 is the center of D6, so it is a normal subgroup of D6. And why H1 is a normal subgroup? The reason is the index of the subgroup H1 is 2, because H1 contains 6 elements and D6 contains 12 elements. So the reason is here H2 is the center of D6, and so this is a normal subgroup of D6, and index of H1 in D6 is 2, and therefore H1 is a normal subgroup of D6. But we claim that our D6 is internal direct product. Sometimes internal direct product is written like this: internal direct product of H1 and H2 sometimes, or more standard notation is this: H1 and H2. Why so? You choose any element from D6. Choose any element from D6 it can be proved that it is a product of an element of H1 and element of H2. So I can leave this as an exercise for you to verify that uh, all these conditions are true. So please verify this. And what is the intersection of H1 and H2? Of course, the trivial subgroup. So once you prove that your D6 is actually H1, H2, you are through. And that is not difficult. You choose any element, you can prove it very easily. Okay. Okay. Next, let us move to some new topic, that is uh, called group action. That is one of the important topics. You will see a lot of applications of group action in algebra. So let us proceed to this. Let us proceed to group action. One thing, let me tell you, fundamental theorem on finite abelian groups. This result I have not touched yet. I will come back to it after some time. Let us finish group action and then I will come to this fundamental theorem a little later. So let us start group action now. Okay, so now group action. Group action. What is group action? Let G be a group G be a group and let capital X be a non-empty set. Okay. An action of G on the non-empty set X is a mapping. This is a mapping from where to where? It is a mapping from G cross X to X, right? And we denote uh, dot of G comma X. Actually, we denote it by G dot X, right? For every G in G and for every X in X, satisfying the following proper conditions. Following conditions. What are the conditions? Number one, G1 dot G2 acting on X is equal to G1 acting on G2 dot X for all G1, G2 belong to G and for all X belongs to X. And number 2, identity element of G acting on X is equal to X for all X belong to X. If there is an action, if there is an action of G on X, we say that G acts on X, or we say X is a G set. Okay. So let us try to understand this definition clearly. What is action? Action, for action you require a group and a non-empty set. The group is denoted by capital G. The set is denoted by capital X. Then action of G on the non-empty set capital X is actually a function. What is the domain of the function? The domain of the function is G Cartesian product X. And what should be the codomain of the function? The codomain is X. If this function satisfies two properties, then we call it as an action of G on X. What are the properties? Means two conditions are to be satisfied. So what are the conditions? Number 1, take any two elements G1 and G2 from capital G and take their product. See, both these functions are looking like dot, but they are different. They are not same. Be careful. I am talking about this. You see, this G1 dot G2, this dot is simply the binary operation in the group. This is binary operation in G. This is the operation with respect to which G is a group. But this dot is not binary operation. This is group action. This dot is defined from G cross X. You have taken two elements G1 and G2 from G. Then G1, G2 is also an element of G. Right? You are taking the action with an arbitrary element X, and the condition says that this must be equal to G1 acting on an element of X. What is that element? G2 dot X. If you are confused, you need not put dot here. So if I do not write dot here, I can directly say G1, G2 dot X. Okay, I should write with black ink. So this may be G1, G2 dot X. Okay, this. The second one is the identity element E acting on any element on X will give you X. So pictorially, if I try to understand this, I have a group. I have a group. This is my G. I have a non-empty set X. Okay. The action is like this. If you take any G from here and if you take any X from here, then dot of G and X will give you an element. So after they operate, means they got operated by the action, they get converted into a single element of X and they will come back to X. So if you choose an element from here, if you choose an element from here, the resultant will also be here. So this is the codomain. And two conditions have to be satisfied, that this is G1, this is G2. Okay, first of all, they form the pair. and they operate on some element x here. This will be exactly same. Suppose after uh, means getting acted by the action, they will come back here. Suppose this is the point. This is some element g1 g2 dot x. But if you take individually g1 operating on x, you may come here, right? If you take g2, you may come here. Now this is an element of x. This is my g2 dot x. If I choose g1 here and if I operate g1 with this element of x, it will be somewhere. This is the same element, this. So this is g1 g2 dot x, and this will be same as g1 acting on g2 acting on x. So these two are same. And if you choose identity from the group, and if you choose any x from here, the action of identity with x will give you back x. So if these two conditions are satisfied, then the mapping dot from g cross x to x is called a group action. And if there is an action of g on x, then we call that gx on x, or x in turn is called a g set. So let us see some precise examples. Only example can make a thing clear for us. So some standard examples, let us see. Examples number 1. Let G be a group and let X be a non-empty set. So this is non-empty. The function dot defined from G cross X to X defined by G dot X is equal to X for all G in G and for all X in X. Is an action, is an action of G on X. Verify. This is a very trivial example. Let us verify. How to verify? You choose two elements. So say G1, G2 in G, and let X belong to X. Then what is G1, G2 acting on X? The definition of this function dot says that whatever element G you choose from G and whatever element X you choose from X, the value of the function on the ordered pair will give you the element of X you have chosen. So by definition, this is X. And this is same as G1 acting on G2 acting on X, because G2 acting on X, G2 dot X will give you X, and G1 dot X is also X. So first condition is trivially verified. If you choose identity, then what happened to identity dot X? By definition it is X. So both the conditions are satisfied. So trivially this is an action. Example number 2. Number 2. The function dot from R cross R2 to R2 defined by G dot x comma y is equal to x plus gy comma y for every g belongs to R and for every xy belongs to R2 is an action of the additive group R plus on R square R2. Now this is a non-trivial example, and here we'll see the difference of the binary operation and the group action, because in the definition both are denoted by dot, so sometimes it creates confusion. Now let us see. Let us verify that really it is an action. So choose two elements from R. Let G. First of all, you see that the function is well defined. First of all, if you take any ordered pair G comma ordered pair XY, then it will go to R2 by this definition. So we have no doubt that any element of the group R plus acting on an element of R2 will produce an element of R2. That is quite clear. Let us choose two elements G1 and G2 from R plus and let us choose an element, arbitrary element xy from R2. Then G1, G2, now it will be G1 plus G2. Now it looks something different. G1 plus G2 acting on this ordered pair xy. By definition, what it will be? You see the definition. Definition says G acting on xy equal to x plus gy. So this will be an element of R2, x plus G1 plus G2 y. Okay. See this y, what is this? This is multiplication in R. There is a multiplication in R. Y, comma, y. Now the group is known to us. We know what are the operations possible there. This is same as, I want to show that this is same as action of G1 on G2 dot xy. I can write this as x1 plus G1y plus G2y comma y. Multiplication distributes over addition in R. From our school days we know, right? Okay, fine. If I consider the first coordinate is x plus G2y, if I consider this plus G2y is my first coordinate, then I can write this as G1 dot x plus G2y comma y. Correct? This is possible because your G will be multiplied with the second coordinate and it will be added with the first coordinate. So G1 dot x plus G2y, y is what? X coordinate will remain unchanged. X plus G2y means not remain unchanged. This will be your x plus G1 times the second one. It will be added. This is equal to G1 dot, what is this? This is nothing but G2 acting on xy. By definition, this is clear. So we are through. So the first condition is satisfied. Okay. What about the second? What is the identity element in R plus? 0. 0 acting on xy. What it will be? By definition, this is x plus 0y, comma y. What is this? This is xy. This is true for all xy in R2. So we are done. So it proves that this function dot is an action. Okay. Let us see another example. Example 3. Examples will make our concept clear. So let X be a non-empty set. The function dot defined from Sx, this is my group, cross X to X, defined by take any permutation sigma dot X is equal to, what is the most natural way of getting an element in X? Just take sigma of X for all X in X and for all sigma in Sx is an action of Sx on X. Let us verify. How to verify? Choose any two permutations. Let sigma 1, sigma 2 be two permutations on X. That is, sigma 1, sigma 2 belong to Sx. And let X belong to capital X. Then sigma 1, sigma 2 means sigma 1 composition sigma 2 acting on X. This is by definition sigma 1, you see the definition. This is sigma 1, sigma 2 as a function of X. Correct? But by definition, this is sigma 1 of sigma 2 of X. That is the definition of composition. This is equal to sigma 1 of sigma 2 X is nothing but sigma 1 acting on sigma 2 of X. But sigma 2 of X is nothing but sigma 2 acting on X. So it is sigma 1 acting on sigma 2 acting on X. So first condition is verified. Second one, see, if E is the identity permutation, is the identity, that is identity function, then what will be the action of E on X? This is identity of X. That means X. The image of any element under the identity function is the same element. So therefore, we are done. Both the conditions are verified. Example 4. Let G be a group. G be a group. The function dot from G cross H. Let us consider okay, 2H defined by G dot H is equal to G inverse for all G belong to G and for all H belong to capital H is an action of G on a normal subgroup H of G. Okay. See, G inverse is always there in H. If you choose G from capital G and H from capital H, because H is a normal subgroup. So initially, if you do not assume H to be a normal subgroup of G, then this function will not be well defined. So there is no question of action. So this action is within the group. That means you have the group, you choose a normal subgroup and then define the action of the group on its normal subgroup by the definition of normal subgroup. Let us verify. Verification is not a problem, or the proof is not a problem indeed. Choose any two elements. Let G1, G2 belong to G and let H belong to capital H. Then G1, G2 acting on H. By definition, this is G1, G2, H, G1, G2 inverse equal to G1, G2, H. G1, G2 whole inverse means G2 inverse, G1 inverse. This is equal to G1, G2H, G2 inverse, G1 inverse. This is equal to G1 acting on G2H, G2 inverse. This is an element of H. But G2H, G2 inverse is nothing but G2 acting on H. So this proves our desired thing. And what happened to identity dot H? By definition, this is E inverse, that is same as H. So this is an action of G on H. Okay. Another example, let us take some different type of example now. So we have seen a similar type of examples, a few examples. Let us choose the example 5. The usual matrix multiplication is an action of GLNR, of the group GLNR on the set of all n by n real matrices How do we denote? We denote it by MNR. So the matrix multiplication is an action of GLNR on MNR. Verify. Take two elements from GLNR, two invertible matrices of order n. So let A, comma B belong to GLNR. And take any n by n real matrix over R and let M belongs to MNR. Belongs to MNR. Then, what is the operation in GLNR? The operation in GLNR is matrix multiplication. And this operation is going to be the action. See the thing. Here, MNR is simply a set. I am not thinking about the set, the group structure of MNR. You know that MNR is a group with respect to matrix addition, but I am not thinking about the group structure of MNR. I am very happy with the non-empty set MNR. The binary operation involved in the group, my group is GLNR, remember. The binary operation involved in the group is matrix multiplication. Correct? So, AB acting on M. What happened to this? This is nothing but the matrix multiplication ABM, because this dot and this dot are same now. And this is same as A acting on BM. And BM is nothing but B dot M. This is easy. And if you take the identity matrix, if this is identity matrix I and N, this is an element of GLNR identity matrix, then I and N, this acting on any n by n real matrix will give you that n by n. This means actually I n cross n multiplied with M, and this will give you M only. So clearly this matrix multiplication is a group action of the group GLNR on MNR. So we have seen enough examples to illustrate the idea of group action. Let us do some theory, let us do some problem, some theorem to understand it, or to see more properties of this definition, why this is so important, or how to get new results from it. So, there is the result. First result regarding group action, it says let G be a group and let X be a non-empty set. We are finding out necessary sufficient condition for the existence of an action of G on X. Then G acts on X if and only if there exists a homomorphism of G into Sx. So see, group action is deeply connected with the permutation group. Let us try to understand the result. You are given a group, you are given a non-empty set. The question is, does there exist an action of G on X? That is the question. How to know that really there exists an action? This question is answered by this result. This result says that if there exists a homomorphism from the group G into the group Sx, given a non-empty set, always you can form a group, that is the partition, the permutation group of that non-empty set. So you have two groups now, one is Sx, another is G. If there exists a homomorphism from G into Sx, then yes, I can define an action. If there is no homomorphism from G onto Sx, I cannot define an action. So this result clearly answers the question, right? And vice versa. So let us prove. Proof. Let G act on X. What is my job? My job is to define a homomorphism. We define F from G to Sx by f of G. What is f of G? F of G must be a permutation, means f of G must be a function from x to x. You cannot express a function unless you define its action. Action means how it acts on element in the domain. Don't confuse with this action with this technical action. So f of G of any element of x, this I define it to be G dot x because you said that there exists an action. And for all G belong to G and for all X belong to X, I claim that F is a homomorphism. We claim that F is a homomorphism. Okay, function is clearly well defined. So let G1, G2 belong to G and let X belong to X. Then what is my claim? F of G1, G2 is equal to F of G1 into F of G2. But all these are permutations. So I have to show that these two agree on every point of X. What is F of G1, G2 of X? By definition, this is G1, G2 acting on X. By the definition of group action, this is G1 acting on G2 acting on X. G1 acting on G2 acting on X means, what is G1 acting on this? Means F of G1 of G2 dot X. Right? G2 dot X is your X. Okay. But what is G2 dot X? G2 dot X is F of of x. Use the definition of composition of function. This is equal to f g1 compose f g2. I need not write because permutation we don't use compose, but still I am writing to avoid confusion. F g2 of x. Since x is arbitrary, these two functions must be same. Therefore, f of g1 g2 must be equal to f of g1 compose f of g2. Therefore, f is a homomorphism. Okay, so I have proved if g acts on x, then there is a homomorphism from g to x to sx. Now, conversely, let f from g to let us change, let us say sigma generally denote permutation, so say phi from g to sx be a homomorphism. Okay, we need to show that g acts on x. Let g belong to g and let x belong to capital X. I have to define an action, remember. We define, okay, let us not write this. We define dot from g cross x to x by, how do I define? G dot x equal to, I have to get an element in x. What is the most natural way to get an element in x? I have to take care of this homomorphism. So phi of g, this is a permutation, right, of x. You will get an element of x for every g in g and for every x in x. Same definition. Prove that it is really an action. So let g1, g2 belong to g and let x belong to x. Then g1, g2 dot x, by definition this is phi of g1, g2 of x, but phi is a permutation, a homomorphism, so it is phi of g1 compose phi of g2 on of x. This is equal to phi of g1 of phi of g2 of x. This is equal to phi of g1 of phi of g2 of x is what? g2 dot x. This is equal to, again by definition, g1 dot g2 dot x. First condition is verified. Second condition. So let E be the identity element in G. Then what is E dot X? By definition, this is phi of E dot X. Phi of E, since this is a homomorphism, remember here we have used the fact since phi is a homomorphism, okay. Now see, phi is a homomorphism from G to Sx. So phi of E must be the identity permutation in Sx. By definition, oh sorry, not dot of X. Phi of X. This is equal to X. Why? Since phi of E is the identity element in Sx, as phi is a homomorphism. Okay, so we are done. Both the conditions are satisfied. Therefore, G acts on X. So this result clearly tells us the story. It actually unveils the picture that when a group will act on a non-empty set. If you can define a homomorphism from the group to the corresponding permutation group of the set, then yes, it is possible to define an action. See, I am saying only it is possible to define an action. I am not saying that it is the only action. Do you follow? What do I say? I say that if there is a homomorphism, if you know that there is a homomorphism F from G to the permutation group Sx, it means I can define an action with the help of F, but it does not mean that that action is the only action. There may be other action also. But if there is no homomorphism, then you cannot have an action from G into G on X. That's the story. So let me stop. Thank you.